Good morning all. So in today's class, we will study about power diodes. So last class, we have seen the introductory part of power electronics, that is EET 306. So there we have seen what is the difference between signal electronics and power electronics and many related things we have seen. So now we will see what do you mean by a power diode, the structure, what is its principle of operation, and then the switching characteristic. So what all things are mentioned in the syllabus, strictly as per the KTU syllabus. Okay, so before introducing to you power diode in detail, I want to explain different types of switches. So power electronics is all about switches. So it is actually power switches. They're actually the workhorses of power electronic system. So switches, as you know, a normal switch, just like a normal switch, a switch can operate in two states: a fully on state, that is the switch will be closed and it will be a conducting state, and fully off state, that is the switch will be open and it will be a blocking state, right? So here you can say that the switch is closed and it is conducting, and here the switch is open. So switch is on, fully closed, switch is off, fully open. So based on this, we can categorize in power electronics. Based on this, we categorize the switches into three types. That is uncontrolled switches, semi-controlled switches, and fully controlled switches. So uncontrolled diode is the best example, because when the switch will be on or off, we cannot control. On or off cannot be controlled. That is the case of diode. And semi-controlled means, output will be, there will be a positive half cycle and negative half cycle, and just like that. So it should be on, the switch should be on and switch should be off, right? So semi-controlled means we can at least control when the switch is on. On can be controlled. So how it is done, all these things we will see. And fully controlled means on and off both can be controlled. On and off both can be controlled. So we can control, we can decide when the switch should be on, so how much part of the output we require, and when the switch should be off, all these things we can control. So uncontrolled, semi-controlled, and fully controlled. So what here we are studying is power diode. In this particular class, we'll be studying about power diode. So diode, basically you have studied from your analog electronics. So this is the basic symbol of a switch. So diode you have already studied from analog electronics. Now here we are studying about power diode. Okay, so the same thing which we have studied now, uncontrolled turn on and off devices. So when it will be on, when it will be off, we cannot control. That is power diode. And controlled turn and off characteristics, that is fully controlled. Transistors, BJT, MOSFET, GTO, all these things we will study. So transistor, BJT will be familiar for you, right? Then controlled turn on and uncontrolled turn off. What will it be? It will be semi-controlled. So this is semi-controlled. So the best example is SCR, silicon controlled rectifier. You will study. Then this is fully controlled, and this is uncontrolled. So you should know these names, very important. Be it an university exam or in your laboratory or any competitive exam, these things are very important. Okay, so now slowly I am bringing you to the subject. So photos of here I have shown you the photos of some power switches. So basically in this module you are studying about power diodes, then power MOSFET and IGBT. So practically how they look. So this is a power diode, this is an IGBT, then this is an IGCT. You study all these things. So now in this module you have studying about power diodes, power MOSFETs, and then IGBT. Okay, so power transistor they have not mentioned in your syllabus, but still before going into IGBT and all, I will be discussing in brief power MOSFET also, because their property is required in IGBT. Okay, so we will start with what you mean by a power diode and how it is different from a normal diode, right? So a power diode has a PIN structure. So a diode has a PN structure. Here we have a PIN, where I is what we call intrinsic. So a power diode has a PIN structure as compared to the signal diode. The signal diode is our normal diode, which you have studied in analog electronics and you have used in the analog lab also, right? Signal diode having PN junction. So there it was PN junction. Here the I in PIN stands for intrinsic semiconductor layer. So if you see, so there is a PN junction. So in between that, there is an N minus layer. That is the intrinsic layer. So that is the intrinsic layer. That is the intrinsic semiconductor layer. So why we need that? So that actually is a break. It's actually, we call that region, that N minus region is called a drift region. So depletion layer also we call. So that layer, it is to bear high level of reverse voltage as compared to the signal diode, the N minus drift region layer is used. So to bear high level of reverse voltage, so reverse recovery voltage, all these things are we are studying in detail. So now coming to the construction. So I told you there is a P plus and N minus layer, right? So N minus layer is actually epitaxially grown. N minus layer is, so this is a term that we are using, epitaxially grown on top of N plus substrate. N plus substrate. So if you see the doping level, N plus the doping level is 10 raised to minus 19 per centimeter cube, whereas for the N minus drift region it is 10 raised to 14, and again it is here it is 10 raised to 19. So this is heavily doped. So in case of a power diode, N plus layer is heavily doped. So this is somewhat lightly doped, and here it is again heavily doped. So this is the anode side and this is the cathode side, and this is the width also. Okay, so this is 10 micrometer to 50 micrometer, and this is the width, WD. Breakdown voltage dependent drift region of thickness WD. So the thickness is given as WD. So I hope this much structure is clear for you, right? So here what actually is one heavily doped P plus layer. So N plus layer was there, then epitaxially N minus 1 layer was grown, then heavily doped P plus layer is diffused on N minus layer to form anode. So P plus layer is diffused on N minus layer to form the anode. So P plus is the anode and N plus is the cathode. So in between we have a separate N minus layer. So that is the difference between PN and PIN. Intrinsic semiconductor layer is there. So we can say there will be a junction J1 will be found between P1 layer and N minus. So here we have a junction J1, P plus and N minus layer, there is a junction J1, right? Because positive and negative, there will be a junction J1 is formed. Okay, so N plus is heavily doped, N minus is moderately doped. So now let's see what is the advantage of having this N plus and N minus layer, and why not just a PN layer, right? That's a very good question. So this is the same figure, a bit more clarity I have given here. N plus is heavily doped, N minus is lightly doped. So if it is given N, it is moderately doped. So here N is not there, it is N minus and N plus, and P plus is again heavily doped. So anode and cathode is there. So why N minus layer? This is a very important question. Why N minus layer? So why N minus layer? So first of all, reverse voltage withstanding capacity, likely I have told you. So voltage handling capacity increases. Voltage handling capacity increases if you are using an N minus layer. So it absorbs the depletion layer of the reverse bias P plus N minus junction. So it absorbs the depletion layer. It absorbs the depletion layer of P plus N minus junction, right? So that is the advantage of using a N minus N minus N plus layer. Okay, and not just a PN layer. I hope the structure is clear for you. Structure and why the use of N minus layer is clear for you. Okay, so then I want to just give you a good comparison also. So a power diode is a type of diode that is commonly used in power electronic circuits. Just like a regular diode, a power diode has two terminals and conducts current in one direction. That's why I told you it's an uncontrolled device. A power diode varies in construction from a standard diode to enable high current rating. That's what I told you. It absorbs the depletion layer and voltage and current handling capacity is increased. So ordinary layer, you know, this is the depletion region, right? PN, and this is the depletion region for an ordinary diode. But what happens here? We are using an N minus layer also, which absorbs, just like I told you, the N minus layer, it absorbs the depletion layer of P plus and N minus junction. So this is a junction formed here, right? I told you this is junction J1 is formed here, so that there will be a depletion layer here, right? So this N minus layer will absorb the depletion region, that depletion region. Okay, so ordinary signal diodes have a junction formed by P-type semiconductor and N-type semiconductor. The lead joining P-type is called anode. We know these things. Another side joining is called N-type. So what do you mean by what is the difference between a normal diode and a power diode? So I think everybody will answer now. So in regular diodes, also known as signal diode, the doping level of both P and N side is same, and hence we get a PN junction. But in power diodes, I already explained, we have a junction formed between a heavily doped P plus and a lightly doped N minus layer, which is epitaxially, very important, epitaxially grown on a heavily doped N plus layer, P plus N minus N plus layer, and this is the drift region. So what I have explained, I am again written here. You can write down the notes also. The N minus layer is the key feature of the power diode, which makes it suitable for high power applications. This layer, so it makes it suitable for high power application. This layer is very lightly doped, almost intrinsic, and hence the device is also known as PIN diode, where I stands for intrinsic. The net charge neutrality of the space charge region is still maintained, as was the case in the signal diode. So net charge neutrality is maintained, because that's why N minus is a bit lightly doped. But the thickness of the space charge region or the depletion region is quite high and deeply penetrated into the N region. So that's the case of PIN diode. Okay. Now, so why this happens? Due to light doping concentration, as the thickness of the space charge region increases with a decrease in the doping concentration. So what is actually happening? The thickness of the space charge region is quite high and deeply penetrated into the N region. You can see it's deeply penetrated into the N region, N minus region. So why it is happening? This is due to the light doping concentration, as the thickness of the space charge region increases with decrease in the doping concentration. So increased thickness of the depletion region or space charge region helps the diode. So what is the main advantage? N minus region. What happens? It helps the diode to block larger reverse biased voltage, and N has a greater breakdown voltage. Region helps to block larger reverse biased voltage. So it has a greater breakdown voltage also. However, adding this N minus layer significantly increase the ohmic resistance. That is one factor of the diode, leading to more heat generation during the forward conduction state. Hence, power diodes come with various mountings for proper heat dissipation. So power diodes, so if you are doing a power electronics project, you will be always using a heat sink. So because the ohmic resistance is increasing, we need proper facilities for heat dissipation. And this actually shows a power diode, a practical diagram of a power diode, which you can find in the industry. So I hope that whatever we have discussed now, so the structure, the different types of switches, everything is clear for you. So now let's see the VA characteristics of power diode. So we have the voltage here, we have the current here. So you can see that when the anode is positive with respect to cathode, so when the anode is positive with respect to cathode, diode is said to be forward biased. You know that. So in this figure, you can see that. So in this figure, you can see that when the diode is forward biased with respect to the, so when the anode is forward biased with respect to the cathode, so initially the current will be rising to a small value, and when it reaches a threshold value, or we call it a cut-in voltage or threshold voltage VT. So beyond that, the current is increasing. So this is the forward conduction current. So after that, it will be increasing. And when the cathode is positive with respect to anode, that is the reverse bias condition. In reverse bias condition, a small reverse current called the leakage current. So a small reverse current called the leakage current will be flowing. So in signal diodes for forward bias region, the current increases exponentially. However, in power diodes, high forward current leads to high ohmic drop, which dominates the exponential growth, and the curve increases almost linearly. The maximum reverse voltage that the diode can withstand is depicted by VRRM. So this is the reverse voltage VRRM, or we also call it peak reverse repetitive voltage. Above this voltage, the reverse current becomes very abruptly high. So that is, the diode will get destroyed. So always the diode should be operated below up in this region. So below the reverse recovery voltage. Above this voltage, the reverse current becomes very high abruptly, and as the diode is not designed to dissipate such a high amount of heat, it may get destroyed. This way voltage is also called the peak inverse voltage, PIV. Okay, so the leakage current is almost independent of the magnitude. This leakage current, which I have mentioned here, is almost independent of the magnitude of the magnitude of the reverse voltage until this voltage reaches the breakdown voltage, that is VRRM. So from there, it will increase abruptly, right? So a comparative figure showing a power diode and signal diode. So you know that for a signal diode, silicon or germanium, it will be, the cut-in voltage normally 0.7 or 0.3 voltage, like that, right? For normal diode, but the forward voltage drop is about 1 volt, around 0.8 to 1 volt for power diodes. And same is the case of in the case of reverse voltages also. So reverse saturation current and reverse voltages. So this is the current. So this is IV Chara. So comparison also I have shown you. Same, but the thing is that it will be a bit more, 1 volt, like that. So the power diodes are now available with forward current rating of 1 ampere to several thousand amperes, and with reverse ratings of 50 volt to 5000 volts. So power diodes, if you check the data sheet, you can see that the current rating is 1 ampere to 1000 amperes, several thousand amperes actually, and voltage is 50 volt to 5000 volt. Okay, so the peak inverse voltage is same as VRRM, or even they have written as VBR. All these things are same only. So now let's see the last topic in this session, that is the reverse recovery Chara, diode reverse recovery characteristic. So whenever the diode is switched off, the current decays from IF. So diode is switched off. So that is after the forward diode current decays to 0, the diode continues to conduct in the reverse direction. So why it is conducting? Because of the pressure of stored charges in the depletion region and the semiconductor layers. So what happens? when the diode is switched off, the current decays from IF. So from IF, the current is decaying from IF to 0 and further continues in the reverse direction due to the charges stored in the space region and the semiconductor region. So just one P plus N minus N plus layer. This reverse current attains a peak IRR and again start approaching 0 value, and finally the diode is off after TRR. So finally the diode is off here at TRR. So it is increasing up to ERR and then again approaches 0 and finally it is off. So what is TRR? The reverse current flows for a time called TRR. So TRR is the time for which the reverse current flows. So this much time in this figure. That is TRR. The diode regains its blocking capacity until reverse recovery current decays to 0. The reverse recovery time TRR. So reverse recovery time TRR is defined as a time between the instant. So TRR can be defined as T. I have written in the next slide, but still explaining here it is good. TRR is time between the instant forward diode current becomes 0. Forward diode current becomes 0 and the instant reverse recovery current decays to 25%. You see, 1/4. And instant IRR becomes 25% of its reverse peak value. Percentage of IRR, that is reverse peak value. So what is IRR? IRR is reverse recovery current. So from IRR, from the maximum to how it is getting reduced 25%, that time is called TRR, that is the reverse recovery time. So same thing I have written here. This time is defined as the reverse recovery time and is defined as a time between the instant forward current reaches 0 and the instant reverse current decays to 25% of IRR. After this time, the diode is said to attain its reverse blocking capacity. See, from here to here. Actually, not becomes 0, not from here to here, but from here, not from the maximum, from 0 to it is becoming that part is called the TRR, reverse recovery time. So then I have some derivation part to be shared with you. From the above figure, we can see that TRR is equal to, so there should be TB is not mentioned here. So TRR is equal to TA plus TB. So reverse recovery times TRR is equal to TA plus TB. The TA is the time when charge from the depletion region is removed. So this much time, the time from the charge from the depletion region is removed, and TB is the time when charge from the semiconductor region is removed. So we have TA and TB here. So TA is actually the time taken for the charge from the depletion region to be same thing. So also from the figure we can say that IRR is equal to TA into di by dt. So this is the figure here. I will just draw here for better clarity. So this is the figure. That is the reverse recovery Chara. Should be very clear with this. We have the figure like this, and this is how roughly it is increasing, right? May not be that beautiful, the figure. So this is IRR. This is 1/4 into IRR. So this is TA. And this much is TB, right? So this is TA and this is TB. So IRR can be written as TA into di by dt. The current is changing, right? So IRR is equal to TA into di by dt, where d by dt is the rate of change of reverse current, right? So this is the rate of change of reverse current. So TA into di by dt, and that is equation number 1. So the area bound by the triangular region in the above figure represents the total charge stored or reverse recovery charge, right? So here you can see a triangular region here. So that area covered is the total charge or the reverse recovery charge QR. So that can be written as half into IRR into TRR. Half into base into height, same thing. Half into IRR into TRR. So but we can also write TA is approximately equal to TRR because TB can be neglected. Okay, TB can be neglected. So approximately equal to TRR. So by putting equation 1 and combining with equation 2, we can write. So here from here we will get TRR is equal to. So here from here you can write IRR is equal to 2 into QR by TRR, and also we have QR is equal to 1 by 2, same thing, same guy here, 2 QR into TRR. So we can write 2 QR by TRR is equal to TRR into DI by dt, right? From equation 1 and 2, we can write 2 QR by TRR is equal to TRR into DI by dt. And so how it will come? So, and also we have IRR is equal to TRR into DI by dt, right? So from here you can write TRR is equal to root of 2 QR by DI by dt. So from here, so in the textbooks all these steps are not given, that's why taking time to derive. So TRR is equal to root of 2 QR by DI by dt. Then putting that, substituting that for IRR, then we will get IRR is equal to TRR into DI by dt, right? So you can substitute and it will be root of 2 QR into DI by dt. That is the reverse recovery current, the same equation, equation number 4. So from equation 3 and 4, we can see that TRR and IRR, that is the reverse recovery current as well as the reverse recovery time, both of them depends upon QR, that is the charge, which in turn depends upon the initial forward diode current IF, right? Initial forward diode current IF. Another interesting parameter defined for power diodes from its turn-off characteristic is softness factor. S factor is very important. So therefore, what's the conclusion here? Therefore, TRR and IRR depends upon DI by dt and QR. So not only QR and DI by dt and DI by dt, and which in turn there depends upon IF, that is the forward current, forward diode current. Okay. So power diodes can only operate for low frequency compared to signal diodes, right? And now another important factor is the S factor, which is given by TB by TA. So TB is the time taken for charge from semiconductor region to be removed, and TA is the time taken for charge from drift or depletion region to be removed. So TB by TA. So if the diode, so in the data sheet you might have seen the S factor, that is the softness factor. If a diode had S factor equal to unity, it is called soft recovery diode. So for S factor less than unity, it is called snappy or fast recovery diode. So S factor indirectly indicates the voltage transient that occurred upon the turn off of the diode. Low S factor implies high transient voltage, while high S factor implies low transient S voltage. Reverse voltage. So S factor, that is S is equal to TB by TA. It's a factor. So the same thing I have just summarized here. So AC voltage is characterized by forward recovery time PF and the reverse recovery time. So in most of the figures, this forward recovery time is not there. So forward recovery time is the time taken by a diode to start conduction is called forward recovery time. So we have studied from the reverse recovery time, TRR only. After the forward diode current decays to 0, the continue to contact in the reverse direction. So we have seen, right, for reverse recovery time, and then slowly it is becoming 25% of IRR. So that part is called reverse recovery time. Instant forward diode current becomes 0 and instant reverse recovery current equals 25%. And what is the reverse recovery time? That time TRR is equal to TA plus TB. So TA, TB separately they have mentioned, and the softness factor also it is mentioned here. So I think we have the Chara is very, so TF is this much, okay? So TF and TRR, so total reverse recovery Chara. So reverse recovery part is up to here, this part only. And one more thing which we can add here is, so if you see the textbook PS Bimbra, they have mentioned another quantity also. I will show here along with this figure. So what actually is the forward voltage? So based on this, how the forward voltage will vary. So how the forward voltage will vary? The forward voltage, which will be like this, right? Then it will go up to the reverse recovery point, and after that, this will be like this. Transient will be. So that is actually the variation of forward voltage drop VF, and then the power loss happening in the diode can also be given as the power loss happening will be like this. So major power loss will be happening during TB. So TB will be the major power loss region. So what is TB? The time taken for the charge from semiconductor region to be removed. So this is the switching Chara, turn on, turn off. So we have seen that the power diodes, they actually take a finite time to switch on and remove the space charge region in the depletion region by large reverse bias voltage during turn off. And during turn off, the excess carriers in the diff region has to be removed first before the metallurgical junction gets reverse bias. So they can be done. The removal of these excess carriers can be done by using recombination or sweep out of reverse diode current. Just common things only I have explained. So what all we have seen? We have seen what is a power diode. How does that differ from a signal diode? So what is the construction of a signal diode, and what extra things we have, extra fittings we have for a power diode? Then the IV Chara of signal diode as well as power diode, and also the reverse recovery Chara of the power diode. All these things we have seen, and this is roughly the symbol. Basically the simple. And if you say, so after finishing the power diode, MOSFET and IGBT, I will be showing one lecture, one small video will be there, which is based on the data sheets. Okay. So if you see the data sheet, you can see IF average, IF RMS, VRRM, I square R, junction temperature, TJ. So there is a junction, right? P plus N minus junction is there. So what is the junction temperature? S factor, IR, all these things will be provided, and also the graph will also be provided, reverse recovery Chara, and then IV Chara, everything will be provided. So this is a simple of power diode. So this basically sums up all the things we have discussed today. Structure is there. Then the basically the cathode anode diagram, IV Chara, then forward bias and reverse bias condition. So based on this only we have drawn this IV Chara, right? Yeah. And then we have the reverse recovery Chara also. That's why I have not included here. So, and then power diodes basically is divided into three types. They are general purpose diodes, fast recovery diodes, and Schottky diodes. So this is basically there. So already I told you it is from 1 ampere to several thousand amperes. So general purpose diodes, the rating is like this, and Schottky diodes is like the normal out diode is up to 100 volt, 1 to 300 ampere. Very high frequency switching power supplies and instrumentation. So metal oxide. So this is construction only. And here fast recovery diode, the topping is done using, because based on the softness factor I told you, no. So all these things is very important regarding the power diodes. So three types. So based on the softness factor, so if S is less than 1, it is a fast recovery diode, right? Okay. So thank you. I hope the power diode session is very well clear for you. Thank you.